Center as its GIS coordinator. And today I'm going to be talking about our new effort toward creating a pre-contact archaeological site predictive model for southeastern South Dakota. And I really appreciate having the opportunity to speak to you all. Thank you so much for coming and letting me talk. So a little bit of background about the project. Archaeological site predictive modeling seeks to predict the likelihood of locations to contain archaeological sites. And what we want the final product of this model to be is basically like a colorized map broken into 30 by 30 meter square areas that will be colorized based on their likelihood to contain archaeological sites. So I was just talking to Rin about this, basically like how you would just sort of, to help you conceptualize this, that you would expect archaeological sites to be found near water. So the way that these rasters, or I guess the maps, looked for Minnesota, because they did this in Minnesota with the MnModel project, which is the template that we're using for this project, as you work your way out from water, the probability gets lower. So then the color on the map kind of transitions from red near water to yellow outside of water. Red being highest likelihood, so like, you know, you can go from having like a high similarity to areas previously established or previously identified as archaeological sites to low probability for areas previously identified as archaeological sites. And how this model that we're creating works is it will be an inductive model as opposed to a deductive model. So we're going to use South Dakota site polygons to create a signature and then try to identify areas on the landscape using statistics that are similar in terms of their location as areas previously identified as archaeological sites, if that makes sense. So our model will be inductive as opposed to deductive. Okay, to continue background, the South Dakota State Historical Society Archaeological Research Center is working on this project with Minnesota State University Mankato's EARTH Systems Laboratory. And so far, the tasks that have been completed are establishing and selecting a modeling region to use as a pilot area, and to create creating a base digital elevation model. Those are two tasks that have already been completed. And then still left to do is condition the digital elevation model. So basically attempt to remove roads and modern infrastructure from the model, so that way it won't bias the goal is to create an approximation of the way the landscape was during the time when pre-contact indigenous folks occupied the landscape. So we're going to work to create a digital elevation model that kind of attempts to recreate those conditions. Finalize site and survey polygons, so we need to remove the overlap between site boundaries and survey polygons to avoid sampling the same area twice. And what was the other thing? I'll get more into that later. And create a hydrographic model, so we want to approximate the way the water was during pre-contact times as well. Create a geomorphological model. So, and how that's going to work is we're just going to use the digital elevation model and some map algebra to attempt to bound particular landscapes. And hopefully that will help with identification of areas similar to those that have been previously identified as archaeological sites. Then we need to update the sampling, intermediate data generation, and statistical modeling scripts to work with the new GIS software. So because the software has changed, the scripts that I currently have access to, or we currently have access to, don't work with the software that we have access to. And then the final step would be to run the site and survey predictive models and create the value raster, or the map that you can colorize. In selecting archaeological sites, the goal is to include only pre-contact indigenous sites, because that's what we're attempting to predict with this model. And that was kind of a more difficult process than I anticipated, just because within our database there are some errors that you have to account for, like some sites had the designation American, but after digging into them, I figured out they're American Indian sites. So that's just one example of like an error that you have to sort of account for. And then dealing with sites that have a depression designation. So like the way that the South Dakota site database works is it's sort of broken down by component. So there are, you would maybe get like 6 results if you type in a specific site number, and one of the components would be depression. So then it would have a depression designation. And that's one thing that I removed, was I didn't take depressions into account because they can't be used to make a determination that the site is pre-contact indigenous, because there are a lot of sites with, I guess, a depressional component that maybe are associated with a dugout or a root cellar or that type of thing. And so now I'll get into creating the modeling regions. And the first step in this process was to compile starting data, and that consisted of the EPA's level 4 ecoregions and the site and survey boundaries. With the idea being that where the ecology across the landscape is consistent, then you would expect human behavior to be similar, or more similar than it is different within that ecological area. And I understand that is a little bit fraught, but it's sort of the best way, or a way of attempting to create a likelihood model. And the step after that is to merge the ecoregions, and that's done where there isn't enough sampling data. And we just kind of used the baseline of there should be 100 archaeological site boundaries within a particular ecological region to allow there to be enough data to create a good statistical model. So where there was like one region with 5 sites next to a region with 75 that had a consistent level 3 ecological classification, we merged the 2 level 4 ecological regions together to create, a region with over 100 archaeological sites. And then the final step was to split ecoregions that covered a really large land area, and that's because to try to create predictions for a really large area, it's very taxing on the computers that we have access to, so we want to diminish region size if there's one, that's maybe going to give us some trouble just based on what the computers that were used to generate the models for MnModel had difficulty with. So here is the region map, the final region map, modeling region map that was derived from the process of consolidating ecoregions and splitting them So the red color indicates the modeling regions with the highest site density. So you see there's a really high site density in the Black Hills. There's a pretty high site density along the Missouri River, and then there's a fairly high site density around Sioux Falls. And one of the things that is in the MnModel documentation is that you tend to have much higher site densities around areas that have been heavily surveyed. So in the Black Hills, you have a lot of public land, federal agencies that are looking at that land all the time, and then you wind up with a higher site density. Along the river, sort of the same thing with river basin surveys, Corps of Engineers, and then around Sioux Falls, you have a big, or I guess, modestly sized metropolitan area, and that results in a higher site density in this portion of the state. So the purple lines right here are indicative of a split between ecoregions that were then merged. So like if there's a black area around a purple line, then you know that that's a place where ecoregions were merged to create a larger modeling region to allow for a big enough sample to create a good statistical prediction. And over here, let's see. Over here, this blue line represents I think it's Vermilion Basin Archaeological Region, I want to say. That was used to split. That was used to split this larger region, just because it had so much area. I figured out that, or just from reading, about the state archaeological regions, that like this was basically the boundary of the Vermilion River catchment. So I thought that's a good place to split because it is kind of an ecological. It does represent an ecological divide, or at least that's my understanding. And then we settled on choosing Les Prairies as our pilot modeling region. So, while doing that, what was taken into account was site and survey densities, not having to condition the Missouri River dams out of the model, or digital elevation model, which would have been really, challenging because you have to like digitize a bunch of contour lines that exist underneath the river to account for, the reservoir, or to try to make the reservoir disappear. You can either do that with like river navigational contour maps, or they have this technology that exists now called bathymetric LiDAR, but that's not present for South Dakota, or at least it's not easily publicly available. So with a pilot project, we decided we wanted to avoid that, having to try to do that. And then we used, as I said before, Minnesota's predictive model as our template. So it was good that the Les Prairies ecoregion was on the border with Minnesota. So there's kind of like probably a much higher likelihood of this process working effectively where it has worked before, or near where it's worked before. So to create a digital elevation model, the goal was to use the oldest available LiDAR data and then mosaic countywide DEMs together to produce, I guess like a very high resolution summary of the landscape, or what the elevation across the landscape looks like, and have it be or show as little development as is possible. So I used the LiDAR data collected in 2008 and 2012, even though it isn't as high resolution as the data that was collected in around 2020 for the area. And this is the final raster. So I'm going to try and use this laser. this area in the southeast that you see actually covers part of Iowa, and then along the eastern edge of this raster, those are Minnesota counties.
The color's a lot better on this one over here.
Oh yeah. I don't know why that is. Yeah, but and then you can see the ecoregion, the pilot ecoregion that we're using, or modeling region that we're using. So with this process, there were some issues that I encountered, or we encountered, and that was that there were chunks of data missing, so we had to fill in those pieces with newer data. Yeah, the Iowa 2008 LiDAR data was really difficult to work with. They didn't have a good tile index, so I had to build my own and just basically pull down pieces of the LiDAR data set and then process them and then see where they popped up in space. And just like, oh, this is number one, and I figured out, oh, the blocks, they're sequential in the block that they're a part of, but you kind of have to figure out or kind of randomly acquire one process piece of the LiDAR data and then have it show up in a block before you can start to sequence everything. And then snapping the digital elevation models together so they're all in alignment and have a consistent row and column cell breakdown. So here you see a missing piece of a digital elevation model with like no data, and I didn't want to interpolate that big of an area because you can see it's about 1/4 of a kilometer, so to just try to guess what it looked like by trying to just like use the area around the gap to fill in, to interpolate and fill in values there. I thought it's going to be way better to just use the newer data, even though it might not be as devoid of infrastructure. So I got a piece of that 2020 data and processed it and created a raster, and that's the final result. So I think it looks, probably a lot like it did in 2008. I don't think that the differences are really that significant. So that process, I think, worked pretty well, but you can sort of see on the edge of this, there's a little bit of a discrepancy. And I think to deal with that, we're going to do some buffering and create no data cells, and then just do a little bit of interpolation, maybe like 3 meters to 5 meters of interpolation, just to make everything match up nice. And then this shows what a raster that's unsnapped looks like. So between counties, you have this issue where the cells aren't in alignment, and if you're going to try to sample cells with points, you don't want there to be that discrepancy. So this is when the raster is unsnapped, and this is when it's snapped. And kind of one of the goals was, this is actually a zoomed in area along a road, and the white area is the road surface, so it's slightly higher than the ditch that you see in blue in the northwest corner. Sometimes it's good to shift the DEM a little bit to make sure that the road is nicely in alignment across county data. And so I did kind of mess with the locations of these rasters a little bit to make them look a little, or to make them mesh a little nicer. And then these now are steps that we need to do to start modeling. So in addition to DEM, we do want to approximate or like basically add the lake bed elevations to the digital elevation models where we can. And the way that, one way that we can do that, and I think the way that we're going to do that, is to use the Game Fish and Parks' lake contour lines to approximate the lake beds. And the reason that we need to approximate the lake beds is because the water levels fluctuate through time across this landscape. So There are some cases where, archaeological sites are inundated, or there are some cases where, in Minnesota, especially doing the Freeborn countywide survey of Minnesota, one thing that we found was archaeological sites seem to be farther away from the current water than you would expect them to be, and that's because the area was so much more inundated in the past than it is now. So that's why it's important to add those lake beds to account for water level fluctuations. And I mentioned before removing roads and mines, and we plan to do this using a cell-by-cell replacement process that just takes surrounding cell values into account to kind of guess what the elevation is across an area that lacks data after we remove it. And then, do that interpolation between mosaic rasters to just kind of smooth everything out. The next step would be is to finalize site and survey polygons, and that is addressing overlapping site and survey polygons to not sample the same area twice. And more emphasis should be placed on more recent archaeological surveys just because of the standards that they need to conform to. So those will be emphasized more. And create a hydrographic model. In order to do that, we will georeference GLO maps and digitize water-related lines and polygons from those GLO maps, with the idea being that these maps are a summary of a landscape less modified by modern agricultural practices. So we want to know, where a lot of the lakes and swamps, or lakes and wetlands were prior to drain tiling, especially, and using the GLO or General Land Office plats as a source will allow us to determine where lakes and rivers and wetlands were before modern agricultural practices were employed here in this modeling region. And we need to code polygons from the National Hydrographic Data Set, National Wetlands Inventory, and those GLO plats for use or exclusion. So we'll kind of try to make our best guess as to which polygon most accurately reflects or bounds a particular water body or wet area. And then incorporation of soils data, and that should allow us to make some educated guesses about where lakes existed thousands of years ago, as opposed to in the 1870s. So here is an example of a georeferenced General Land Office plat, and you can see a lake there, kind of in the middle of the map. So we're going to bound that with a polygon, and this isn't the same plat, but this just gives you an idea. So here is a wetland bound with a polygon that we'll use, in our model. Wet areas may have been used as water sources. It's kind of the premise. And this could have been a lake, prehistorically at one point, in closer proximity time-wise to when the area was glaciated. And creating a geomorphological model is another important step, and we plan to use Washington's predictive modeling method, where they derived landscape bounds from digital elevation model and math. And then we're going to try to use Terrex software for terrace classification, because those are really important landforms for predicting where archaeological sites are. And then update the scripts, so migrate the scripts from Python 2.7 to Python 3 so they can be used in ArcGIS Pro, and then exclude unused variables from the R scripts that we got from the MnModel project, and those use a random forest statistical method. The ins and outs of that are still murky to me, but I think I have the concepts, in my head. And yeah, we're going to work toward changing those scripts to exclude the variables that don't exist for South Dakota and do exist for Minnesota. There's just so much more data available in Minnesota for use in a project like this. And as discussion, the hope is to complete this pilot within 1 year. So hopefully by this time next year, we'll have a value raster for the West Prairies modeling region. And yeah, we're going to try and make our data reflect these previously existing landscapes to the best extent we're able to accomplish the goal of producing a good likelihood of archaeological site classification map that we can. We're going to produce the best one that we can by improving or making the data reflect how the landscape was. And here are my references. And if there's time, feedback is appreciated. Yeah.
How much do you rely on some of this modeling of the Aeros data center and space pictures and photography and stuff? I see this squaring up, matching a lot of the survey. So, what decade or whatever was a lot of this land surveyed?
Oh, by the General Land Office?
Yeah.
That was done in the 1870s, primarily in South Dakota. I think the initial platting took place from the late 1860s on into the 1870s.
How about the satellite? Is that helping you some? Picturing and something?
Well, so the data that we're using most is LiDAR data, and that's collected by plane flyover, and the plane shoots lasers at the ground, and then based on a mathematical calculation of the speed of light and time it takes for the laser to return, then you get a distance, and if you know the altitude of the plane and the angle that the laser is shot at, then you can. That's how they collect the elevation data. And for the area that we're looking at, that data was first collected in 2008 and 2012, and it can be used pretty effectively to generate 1 by 1 meter areas elevation across space. But they have gone back and collected more, and it's been more coordinated, so you don't run into the gap issues anymore, because when they first collected the data, I think that they were doing it as individual counties. So in a lot of cases, the county data just doesn't match up, or it might not be of a consistent quality. But now, they're I think they're doing federal coordination. I don't know to what degree they're collaborating with, the feds are collaborating with counties, but I think that that's happening. And now, you can process the data at, I want to say about a foot or like a third of a meter. So it's much higher resolution now than it was in 2008 and 2012. But for this project, the older data works better just because there are more highways, or there are bigger highways now. There's more places on the landscape that are less likely to reflect what it was like prehistorically.
I've got a real good friend and neighbor. He's an avid watcher of the skies. I label him, and he watches the flights and stuff coming across the nation. And we were standing outside in his yard one day, and I've seen it even in my own yard. They must be mapping some of these areas now, because just recently, because this plane would fly due north, south-north trajectory, and in an hour or so, here they'd come back the opposite direction. So
yeah, that could very well have been a LiDAR collection project. Yeah.
That was, I saw an article on that. It is being done. We're noting that you might be seeing low-flying planes collecting geographic data over this part of the state. I don't know where else. I don't even know who's collecting it.
Well, it's interesting, thank you.
Were you stretching or?
I'm curious, so you've got digital soil data too?
Yeah,
And how does that correspond to like your USDA soil manual? Is it fine grained, is that? Or?
Yeah, I think it's a little bit higher resolution than that. But it's pretty much just a digitization of all these surveys. And you probably know about that, George. You know.
I think that's right. They just took the existing surveys.
Okay.
Yeah, but they continue to do them, so I think they're doing, they have a little bit better idea of where they're at just because of improvements in GPS technology. Yeah, that's, it's just like your soil manual that you can pop into mapping software, basically. Okay, thank you so much.